Tack fusing is an effective method for creating textured works in kiln-formed glass. In tack fusing, glass is fired within a range that creates enough heat work for the material to fuse while maintaining the desired amount of form and texture. Tack fusing often results in pieces with varying thicknesses. This raises technical issues. In this lesson, you'll learn the effects of firing to different tack fuse temperatures. We'll also cover firing schedule considerations to avoid thermal shock and promote effective annealing. Finally, we'll follow a project through tack fuse and slump firings. When designing tack-fused works, it's helpful to know what to expect when firing to different temperatures and the effects of cumulative heat work. Tack-fuse process temperatures generally range from 1250 to 1450 degrees Fahrenheit. Constructing a tack fuse with two base sheets in a single firing results in flat bubbles where the layers have not fully fused. If this isn't what you want, consider taking a multiple firing approach. Full fuse 2 layers of 3mm sheet glass to make a base and follow with a lower tack fuse firing. Let's look at the effects of firing this test piece, composed on a pre-fused 6mm base sheet with an assortment of sheet and accessory glasses. Fired to the low end of the process temperature range, tack-fused elements have sintered or heated just enough to adhere while maintaining much of their original form. Fired to the high end, the elements are more fully fused to the base and have softer edges. For greater variation in effects, use a sequence of multiple tack-fuse firings, moving from higher to lower process temperatures. In this piece, sheet glass design elements were tack-fused to 1425. Then frit was added before an additional firing to 1325. Note that light applications of fine glass, such as powder and fine-line stringer, will soften and flatten at the hotter end of this temperature range. Coarser frits and larger materials will remain in higher relief. Reactions, such as in this copper and sulfur-bearing combination, will be less developed or not present at all in low-temperature tack-fuse firings. This is especially true when compared to firing to a full fuse. Note that strikers may not fully develop their target color at a tack-fusing temperature, especially at the lower end of the range. Here we use transparent orange. It's important to keep in mind that heat work is cumulative. This means that the more times a glass is fired, the more likely it is to change in some way. And note that each firing can affect any new materials applied, as well as the materials that have already been fired. There are endless effects to explore firing in this temperature range, considering different techniques, forms, and combinations of material. To prevent thermal shock and ensure proper annealing, pieces with uneven thicknesses require specific modifications to the firing schedule. Let's walk through the decision-making process for firing this light diffuser. We'll start by firing 2 layers of opaline to a full fuse. Next, we'll add 6mm clear sheet glass design elements. Because the base is a solid piece, we've slowed the initial rate of heat to a conservative 300 degrees per hour. The goal is to avoid thermal shock, which can occur when firing too rapidly. Again, since the base is a solid piece, there's no need for a hold at 1225 to squeeze air from between the layers. Instead, we'll choose a short hold at 1000 degrees. This brings the piece past where it could thermal shock and unifies the temperature within the body of glass. The second segment ramps up to the process temperature, in this case 1425 with a 10-minute hold. The third segment encompasses the anneal hold at 900 degrees. We'll determine the duration by the thickness of the project. Using the annealing chart for thick slabs, we'll select an anneal soak time for a piece that is twice the thickness of the thickest area of this piece. This longer hold promotes a uniform temperature throughout, which is necessary for proper annealing. Calculate this by adding up the thickness of the components. For this project, the thickest area is 12 millimeters, so we'll double that and follow the chart for a thickness of 24 millimeters. Use the annealing chart to determine the rest of the cycle. Slower cooling allows the thinner areas to cool at the same rate as the thicker areas. This minimizes annealing strain and lowers the likelihood of thermal shock. Next, we'll add more design elements and then fire to a lower temperature to create a light diffusing effect. Once again, we'll use the annealing chart for thick slabs as a guide for reheating the tack-fused piece. To determine the initial rate of heat, refer back to the final rate of cooling for twice the thickness of the thickest area. In this case, the rate is 162 degrees per hour to 1000 with a 20-minute hold, then 600 degrees per hour to a process temperature of 1335 with a hold for 10 minutes. We do this to approximate the same effect as firing at a faster rate to 1350. This is because the insulating materials of the kiln will have more time to absorb heat due to this slower rate. This will cause slower cooling from process temperature, resulting in more cumulative heat work. As the thickest area has not changed, we'll again follow the annealing chart for 24 millimeters to anneal and cool the piece. Now we're ready to slump the piece. We'll follow the guidelines we've established in the early firings, using a process temperature of 1180 with a 5-minute hold. In the finished piece, tack-fused elements interact with both reflected and transmitted light. In addition to creating textures in the kiln, tack-fused techniques can also introduce lensing and other optical effects. Tack fusing makes a variety of textured works possible. A solid understanding of the effects of cumulative heat work and strategies for firing effectively can help you achieve your artistic vision.